When a chemical reaction occurs, heat energy is transferred between the system and the surroundings, so thermochemistry can be defined as the study of heat changes. The quantity of heat is called the heat of reaction, and it's measured in a calorimeter. Here's a bomb calorimeter. This will measure the heat of combustion for a sample. What we're going to do is take a sample. We're going to place it inside the bomb, which is just a stainless steel container. We're going to fill this container with oxygen. And we're going to combust the sample. When we combust the sample, we're going to produce CO2 and water. The combustion will also produce heat. The heat is either absorbed by the bomb, which is this stainless steel container, or heat is absorbed by the water. Well, by getting the increase in temperature, along with some other factors, we can measure the heat of combustion for the sample. So let's look at a problem. We're combusting methanol, and we want to know the molar heat of combustion of methanol. So I want the joules per mole for methanol. Well, the heat produced from the reaction is either absorbed by the bomb calorimeter or it's absorbed by the water. So let's do qcal first. We're going to take the heat capacity of the calorimeter times the change in temperature. The heat capacity, I'm going to change this to joules per degree Celsius, 1060, and then delta T goes from 23.1 to 25.9, so delta T is 2.8 degrees Celsius. So the bomb will absorb 2,970 joules of heat. Now the water will also absorb some heat. MC delta T, we have 1,350 grams of water. Specific heat is 4.184 joules per gram degree Celsius. Delta T is 2.8. So the water absorbs 15,800 joules of heat. Add those together. Total, they absorb 18,800 joules. We have 0.828 grams of methanol. The molar mass of methanol is 32. So that means we have 0.0259 moles of methanol. I want the heat of combustion for methanol. So we're going to take the amount of joules, which is 18,800. Now I'm going to make this negative because the reaction is actually exothermic. The water in the calorimeter absorbed 18,800 joules, but the reaction itself is exothermic, so I'm going to make the heat of combustion negative. I'm going to divide by the moles of methanol, and we have my molar heat of combustion for methanol, negative 7.26 10 to the 5th units joules per mole. In a bomb calorimeter, the volume is constant, and so there's no work of expansion done. If we go back to the first law of thermodynamics, if there's no work done, delta E, which is the change in internal energy, equals Q, which is heat. If a reaction is carried out in a container open to the atmosphere, like in a beaker, the heat of reaction is called the enthalpy change, delta H. So if we're at a constant pressure process, delta H equals Q, where delta H is enthalpy. Any property of a system that depends only on its state and is independent of how the system got to that state is called a state function. For example, if we want to go from, in this case, state 1, which is the bottom of the mountain, to state 2, which is the top of the mountain, there are multiple ways we could get there. We could go in a straighter line path, like path A, or we can kind of go in a zigzag path, like path B. It doesn't matter how we get to the top of the mountain. That would be a state function. Well, enthalpy is a state function. It doesn't matter how we get from state 1 to state 2. It just matters that we're in that state at that particular moment. So enthalpy is a state function. Now, heat and work are not state functions, because heat and work depend on how we get there. Heat can be positive or negative depending on whether heat is absorbed or released by the system. Same thing with work. Work can be positive or negative depending on if the system is doing the work or the system is receiving the work from the surroundings. So enthalpy, delta H, is a state function. Q and W are not state functions. So again, when you look at thermochemical equations, delta H is enthalpy, but it's heat. If delta H is negative, it's exothermic. If delta H is positive, it's endothermic process. Hess's law says if a process can be considered to occur in steps, the enthalpy change for the overall process can be obtained by summing the enthalpy changes for the individual steps. Let's look at a couple problems with Hess's law. We're given two equations up here along with their enthalpy values, their heat values. We want to determine the enthalpy change for this reaction, N2 plus 2O2 forming 2NO2. So that's my overall reaction. I want to find delta H. What I do is I start over here on the left and I see N2. Well, I go back to my two equations that I'm given. I see N2. It's a reactant, so I'm going to write that as is. Delta H for this reaction is 180.74 kilojoules. And then I notice I have two NO2s on the product side, and you go back up to my two example equations and I have 2 NO2 on the product side. So I'm going to rewrite that equation as is. Delta H is negative 113.04. You'll notice that 2NO is a product in the first equation, but it's a reactant in the second equation. It cancels out. Everything else adds up to give me my overall equation. N2 plus 2 O2s form 2NO2. So Hess's law says if this process occurs in steps, simply add up the steps. So I'm simply going to add 180.74 plus a negative 113. So delta H for the overall reaction in this case is a positive 67.7 kilojoules. Okay, that one wasn't too bad. Let's look at this one. Start down here with my final. 3C plus 4H2, that's what I want to determine. C3H8. And I'm given three different equations. Well, I'm going to start here with my reactant. I see 3 carbon. Well, you go back up to these equations. There's carbon here in this second one, but I need 3 carbon. So I'm going to take this second reaction, and I'm going to multiply it by 3, which means delta H, which is negative 393.5, is also multiplied by 3. That will give me 3 carbon. My next one, 4H2. Go back up to my equations. I have 2H2. So I'm going to write that equation, 2H2 plus O2 forming 2 water. But I need 4 H2s, so I'm going to multiply that by 2. So that means delta H which was negative 571.6, gets multiplied by 2. Then finally, I have C3H8 as a product. We'll go back to my examples. I have C3H8, but it's a reactant. So I need to flip that equation around. So the 3CO2 plus 4H2O are reactants, and C3H8 and 5O2 are products. When I flip an equation around, delta H changes signs. So in this case, delta H would be positive 2,220.1 kilojoules. Now before I add up those numbers, you want to make sure everything that's not in this final equation down here cancels. So we have 3C, 4H2, and C3H8. Everything else should cancel. If you look at the CO2s, they have 3 CO2s here, we have 3 CO2s here. They cancel. If you look at water, I have 4 water here, I have 4 water here on the reactant side. They cancel. If you look at oxygen, I've got 3 oxygen here and 2 oxygen, so that's a total of 5 oxygen on the reactant side. Well, I have 5 oxygen on the product side, so all of the oxygen cancel out. So everything else will add up to give my final equation. So Hess's law says simply add those 3 delta H values together to get the enthalpy change for the overall reaction, which comes out to negative 103.6 kilojoules. So Hess's law is simply manipulating equations to give you what you're looking for.